AP Physics, this is summer lesson number 11. It's on net force. It's just a few more applications of force. So, Anna pushes a 3 kilogram box with 17 newtons of force. A 5 newton friction force opposes the motion. At what rate does the box accelerate? So the first thing you do is you find the net force, and that's going to be the pushing force minus the friction force. So 17 minus 5. That will give you 12 newtons. That's called the net force, and that's usually designated as F sub net, or maybe just F sub n in many cases. So now you're looking for acceleration. You have your net force, 12 newtons, and the mass, 3 kilograms. So you start with F equals ma, and you solve for a. So solving for equations is going to be a skill that you need to develop in this class. So it's F divided by m equals a. Divide both sides by m, and you get a equals F net over m. And now you just plug in the numbers. 12 divided by 3 is 4 meters per second per second. If a force goes around a pulley, a wheel that guides the rope, the pulley does not change the value of the force. So Stick Boy holds a 5 kilogram box using a rope run over a pulley. How much force did he exert on the rope to hold the mass? Well, the downward weight of the force of the rope is weight equals mass, 5 kilograms, times gravitational acceleration, 10 meters per second. Remember, W equals mg is just a special case of F equals ma. And so the weight is 5 kilograms times 10 meters per second squared. That gives you a weight of 50 newtons. Since the box is stationary, Stick Boy's pulling force must balance the weight of 50 newtons, so Stick Boy is pulling with 50 newtons of force. So here we see Hercules, and Hercules is pushing with 500 newtons of force to the right. So the acceleration is in the direction of the force. Acceleration is always in the direction of the force in a situation like this. So then the question is, Hercules is putting an unbalanced force of 500 newtons on the block above. Can you tell which way the block is moving? And the answer is no, you cannot tell which way the block is moving. The block does not need to be moving in the direction of the force. You must first know which way the block is moving at the time Hercules applies the force. So how is that? How does that make sense? Imagine that block is a big heavy car and it's moving towards Hercules. And when Hercules puts that 500 newtons of force on it, the car, or the block in this case, is not going to stop immediately. It's heavy. It's going to push him backwards. So even though he's putting a force to the right, the block will continue to move to the left for a little while until he can bring it to a stop. So that's a very important point to remember, is that the motion of the object does not have to be in the direction of the force applied to it. It might be, it might not be. So let's look at some of the different situations. What you can tell is this. If the block is standing still and Hercules puts a net force of 500 newtons to the right, then the block will speed up to the right. Remember, a net force is going to cause the block to accelerate. If the block is already moving to the right, that's the direction of the force, then it will speed up even more going to the right. If the block is moving to the left, that's against Hercules, that's the example of the big heavy car moving towards Hercules, then what Hercules will be doing is slowing it down. So his force to the right will cause that block, if it's already moving to the left, to slow down. Now what will happen is, if he continues to put the 500 newton force on, he'll slow the block down, moving to the left until he finally brings it to a stop. And then if he continues to put the 500 newton force on, he doesn't stop, then it will start to speed up or accelerate to the right. So slows down to the left, speeds up to the right. And 4, if the block is moving in any other direction except toward or away from Hercules, so imagine it's moving out of the screen directly towards you, then it will be curving. So if that block is moving at a steady velocity, because we didn't say there was any force in the forward backward direction, that is toward you or away from you, but let's say it's moving toward you at a constant velocity, then he starts pushing it to the right. That block is going to come towards your face, but he's going to be pushing it to your right. So that block is going to curve away from you to your right. Friction force is a force that opposes motion by one object contacting another object. Example, when you push your desk across the floor, it resists moving because of friction force of the desk on the floor. So here you see Stick Girl is pulling that box to the right, but the friction force of the box against the floor is causing it, is resisting that. That's a force against her pulling force. So the net force in this instant is Stick Girl's pulling force minus the friction force. Now, does friction force always cause something to stop moving? Not necessarily. When you walk, think about what's happening with your foot against the ground. You're pushing back with your foot as you're walking. But the friction force of the ground is the reactive force that's pushing you forward. That's what causes you to go forward. Think about this. What if you were on very slick ice and your foot, you pushed it backwards while walking on ice? Your foot would just slip. There would be no friction force of your foot against the ice, and therefore you wouldn't move forward. You just keep slipping and slipping and slipping. So if there's no friction force to react against your foot pushing backwards, there's no friction force to push you forwards, then you're not going to move forwards. So when we said that from the times of the Greeks to Isaac Newton that everybody thought something needed a force to keep going, the main reason is because of friction force. Every time you push any object here on Earth, it's going to come to a stop because of friction forces eventually. But if you're in outer space and you push an object, and this is what Newton is saying, and there's no friction forces to oppose you, then once you push an object, it'll keep going forever and ever and ever, unless it crashes into a star or something. So it takes a force, usually a friction force, to oppose the motion to cause something to come to a stop. Okay, so that takes care of a little lesson on net forces. You'll see all kinds of net forces in this class, every variety throughout the rest of this class.